Here in this video, we would like to talk about Kirchhoff's second law or Kirchhoff's voltage law, which is also called something like KVL. This law helps to find out the current at a particular point of a circuit. So what is this Kirchhoff second law or Kirchhoff voltage law tells you is the definition. The algebraic sum of potential differences in any closed circuit or a closed loop is equal to 0. So that is just a statement. We shall try to understand what's the meaning of that statement is. Anyway, let me reiterate the statement once again. The algebraic sum of potential differences in any closed circuit is equal to 0. Before going further, it's very clear that this can be applied only for any closed circuit or a closed loop. So the precondition to apply the Kirchhoff's voltage law is we shall be talking about a closed circuit or a closed loop. If it is something is open, we cannot apply the Kirchhoff's voltage law. So what does it mean by? It says that, let me draw a circuit and show you what is the meaning of that. Let's imagine there is a battery. Let the EMF of that battery is equal to E. Let there are some resistors, say for example R1 and R2 connected to that battery as shown. Assume the battery is an ideal battery and its internal resistance is equal to 0. So it says that the algebraic sum of potential differences in this closed circuit, this is a closed circuit because there is no place open and the current is passing. How does the current is passing? From the positive plate of a battery, current starts, will go across R1 and then go across R2, comes back to the negative plate of the battery and the circuit is completed, and that will be keep on happening. So it's a closed circuit. So in this closed circuit, the algebraic sum of potential differences. Whenever we say algebraic sum, some of them has to be treated like positive and some of them has to be treated like negative. So let us see what are that is, right? So when you connect two resistors like this EMF E is very clear that they are passing, current is passing like this. So they are in series, current remains the same and the voltage is distributed. What is that value of the voltage? Let the voltage drop across the first one equal to V1, second one equal to V2. So a simple law, even without talking about a Kirchhoff law, tells you that the total EMF supplied by the battery is voltage across the first one and voltage across the second one. So voltage across the first one according to the Ohm's law can be written like IR. That value of that R is R1 here and I R2. This is R2. So this is kind of a conclusion can be drawn without getting into the Kirchhoff law itself, because the circuit is a simple circuit. But if the circuit is a complicated circuit, it becomes difficult to identify who is in series with what and how the current flow is happening. That's why there is a Kirchhoff voltage law. So to say the same thing like we have said E equal to voltage 1 plus voltage 2, we have a law called voltage law, Kirchhoff's voltage law. So what it tells you is some of the EMFs has to be treated like positive and some other EMF has to be treated like negative. For that, first of all, so what are the conditions for the Kirchhoff law is condition number 1. The loop shall be closed. There shall be a closed loop or a closed circuit. That's the first condition. And we shall have a kind of a sign convention. For that sign convention, we shall consider a loop. We shall consider a closed loop. Inside the closed loop, either in clockwise or in anti-clockwise. It could be anything. There is no rule that we shall choose only clockwise or we need to choose only anti-clockwise. You can choose any of that, but the only condition is within a given problem, if you need to choose the direction twice, both the times you shall choose the same, either clockwise or anti-clockwise. For one part of the problem clockwise, for the other part of the problem if you choose anti-clockwise, you are going to get a wrong answer. The only condition is we shall choose either clockwise or anti-clockwise throughout the problem. So within this circuit, let me consider a direction, a loop. So I have chosen a clockwise. I can choose even anti-clockwise also, but I have chosen clockwise just for the sake of convenience. I will also choose anti-clockwise and write the equation at the later time. So you can see this is the clockwise direction you have chosen, and this is how the current is passing. In the resistance R1, current is passing in the same clockwise direction that I have chosen. So the first condition is if current is passing in the same direction of the loop that we have chosen, that we have initially chosen, treat that potential drop across that element as negative. So be careful. So, and of course obviously vice versa. What do you mean by vice versa? If the current is passing in a resistor in opposite direction to the loop chosen, treat that EMF as positive. In the same direction means negative, in the opposite direction means positive, right? That's the one condition. So let's try to apply that here. See here, this is the direction of the current that is passing because current passes from the positive plate of the battery. This is the direction of the loop that we have chosen. Both of them are in the same direction. So the potential drop across that is a positive. So across that is a negative as per the rule. Even look at the second resistor. This is the direction of the closed loop we have chosen. This is the direction of the current that is passing. So that is also negative. If the current is passing in the same direction of the chosen direction, treat that potential drop as negative. Now it comes to the cells. How shall we handle the cells? In the chosen direction, you have chosen a clockwise or anti-clockwise, right? In the chosen direction, if you get negative plate of the battery first negative plate and then positive plate. If you get the negative plate of the battery first, treat that EMF as positive. Means what? In the chosen direction, if you get the positive plate of the battery first, then treat that EMF as a negative. See here, you are going in this way. In the clockwise direction you have chosen. You got the negative plate of the battery first. After that, in the chosen direction, you are crossing the positive plate of the battery. So this EMF shall be treated like a positive, right? Let us try to apply all these rules and see how does it looks like. So these are the rules. What are the rules are? Loop shall be a closed loop. Consider a direction either clockwise or anti-clockwise. If you have chosen a direction and the current is passing in the same direction across any element, treat the potential drop across that element as negative and vice versa. In the chosen direction, if you get the negative plate of the battery first and then positive plate of the battery, treat that EMF as positive and vice versa, right? Let us try to apply them to the given circuit and see what happens. So look at this. R1. Current is passing in this direction and this is the same direction we have chosen in a clockwise direction. So the potential drop across that shall be negative as per that. The same direction means negative. So minus IR1, because as per the Ohm's law, potential drop equal to IR. Now look at this second part. Current is passing in the direction and the chosen direction clockwise are also the same. Therefore, that potential drop is also negative. Minus IR2. And look at the battery. You are going in this direction. Then you are first facing the negative plate of the battery and then the positive plate of the battery. So if you get negative plate of the battery first, treat that EMF as a positive. Plus EMF E equal to 0. This is what you mean by the algebraic sum of potential differences in a closed circuit is equal to 0. In the other sense, you take these two values to the other side of the equation, you will get E as a IR1 and IR2 is the same as the equation that we have written in the beginning basing on the basic concepts of current. So this concept is used to solve the tougher problems or problems with a lot of criticality when compared with the Ohm's law. Now, just for the sake of convenience, what I will do is, what happens if I choose an anti-clockwise direction? I will just discuss that here, right? So I will take the same diagram, but this time I am not going to choose a clockwise direction, but I will choose an anti-clockwise direction and show you what kind of equation you will get it. So this is R1, this is R2. Both of them are connected to a battery of EMF E. Let us see first of all how the current is getting distributed. From the positive plate of the battery, current I starts. It will go to the R1 and then to the R2 and comes back to the negative plate of the battery and the circuit is completed, and that will keep on happening. Now you shall choose either a clockwise or anti-clockwise direction. Here I have chosen a clockwise direction. So just to tell you that it's not going to be any issue, I will here choose anti-clockwise direction. So it's an anti-clockwise direction. This is what do you mean by anti-clockwise direction, right? So you can choose either a clockwise or anti-clockwise. Here I have chosen an anti-clockwise, right? Now look at that. Now look at the flow of the current. Across the first resistor, current is going like this. This is the anti-clockwise direction that you have chosen. Both are in opposite, right? So look at the formula. Look at the concept, right? If the current is passing in the same direction, treat that potential drop as negative. And vice versa. That means what? If the current is passing in the opposite direction, treat that potential drop as a positive. Here they are in the opposite direction. Therefore, I will write plus IR1, right? Look at the other one. This is how the current is passing in the second resistor, and this is what our anti-clockwise direction is. Again, both of them are in the opposite direction. Therefore, that potential drop is also positive, plus IR2. And look at the battery. This is your anti-clockwise direction. This is how you are going. And if you look little carefully while you are going like this, first you get this is how you are going, right? So first you will get the positive plate of the battery and then the negative plate of the battery. So look at the formula. In a chosen direction, if you got the negative plate of the battery first, treat that EMF as positive and vice versa. Now you got the positive plate of the battery first. When you get negative plate, EMF is positive. When you get the positive plate first, you are going this way anti-clockwise and you are getting the positive plate of the battery first. Treat that EMF as a negative opposite to that, minus E equal to 0. So take this E to the other side, it becomes IR1 plus IR2 equal to E. This is also the same equation. So if you look at this equation, this equation, this equation, all are same. So that is, so the Kirchhoff law is kind of an advanced law of the Ohm's law to solve complex circuits, and Ohm's law can be further even used even after this, learning this, for a simple circuits. That's what you mean by Kirchhoff's voltage law, right? Thank you for watching.